We're looking at interference. We talked last lesson about coherence and what coherence is. It's two waves, not necessarily in phase, but having the same frequency and having a constant phase relationship between them. We mentioned this equation again. We're looking at light as a wave. So in the case we regard light as travelling at one speed c. That's the speed of light in a vacuum, of course, equal to the frequency multiplied by the wavelength. And so also I may talk in wavelength or frequency. Frequency is inversely proportional to the wavelength. As the frequency increases, the wavelength decreases, of course. Here's a diagram of two waves in superposition, one over the other, and what we see here is that this wave is out of phase by around about a quarter of a wavelength, maybe a little bit less than that. That's all right. I read. Remind me to give you a textbook. Yeah, you ordered a textbook, did you? Do you remember? Yeah, I think you did. Yeah. So these two waves here have a constant phase relationship. We would see interference occurring here, and whether it be constructive or destructive, this situation here where two waves occupy the same space at the same time doesn't really exist, because what we would see is a change in these two waves as a result. What would happen? Yes. Yeah, we're likely to see some constructive interference here, and so the wave's amplitude would increase. Okay. We looked at monochromatic light sources. Monochromatic light sources are those which have one specific wavelength or one specific frequency. Incandescent light sources are not monochromatic. We look at this diagram here where we see regions of destructive interference and constructive interference. And we also talked about path difference. So there's two sources here. You could imagine these as if two stones were thrown into the water at exactly the same time, or dropped into the water at exactly the same time. And the waves that result, of course, interfere with each other. So the waves from source 2 have reached this far. The waves from source 1 have reached this far. And in this area here, this eye-shaped area here, they are interfering with each other. They occupy the same space at the same time. You can consider the dashed lines here troughs, and the solid lines as crests. And so we looked at the fact that there's a crest, one crest, two crests, three crests to the center line here, this line AB. And once again, also from source 1, one crest, two crests, three crests also. And so the path difference between these two sources to that point there is 0. It's exactly the same distance. Then we looked at the path difference here. So have a look at this line here. So another AB line through here. And we can see that there's one crest from source 2, two crests from source 2, three crests from source 2 to that point there. From source 1, we have one crest, two crests, three crests, four crests to that point. So the path difference between the two sources to that point is, of course, one wavelength. All right? And so on and so forth. Have a look here through these regions PQ. I've drawn them with red dots. You can see here a crest and a trough intersecting, and so we would have destructive interference along this line through here. Okay, and you might see, what do we get from here? We get a trough. So imagine, okay, so here's half a wavelength. Okay, 1.5 wavelengths, 2.5 wavelengths, 3.5 wavelengths, 4.5 wavelengths to that point there from source 2, and from source 1, 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, 5 wavelengths. So through this region here, PQ, P1, Q1, we have a path difference of half a wavelength. We started to talk about diffraction, and hang on a second, what have I done here? 50%. Oh, okay. Here's a diagram of what diffraction looks like of water waves around an obstacle. So we have plane wave fronts moving in this direction through here. When they encounter this aperture here, which is comparable to the width of the wavelength, we see a bending of the wave around as it passes through that aperture. And notice this obstacle here. You could consider this here an obstacle. The waves pass through here. They bend around the obstacle also. And here's another obstacle here. So these already diffracted waves diffract again, and they bend even further around this obstacle. And this is how we get these curved bay-type beaches on the coast of any country. Question? When it's not similar to the wavelength of the wave. So this distance here, the distance between those two areas where the wave just cannot pass through, it's hard to see what the wavelength of the waves is here, but the closer that this distance is here to the wavelength, the more bending we're going to see. Okay, is that clear? Yeah. And we see that here. So plane wave fronts coming in, they encounter an obstacle and they bend. If the obstacle is much closer to the wavelength of the wave, then we might see a bending which is more noticeable, perhaps, than what is in the diagram that was there already. Here's a diffraction pattern. So you'll notice that the region of, we have plane wave fronts coming here in this way. They encounter an obstacle, which is an aperture. They diffract through that aperture, and of course they continue doing that all the way until they reach this screen. And if we're talking about light, of course we can't see this light. There's no way to see it unless we put some obstacle in the way or something that will reflect the light. And so we say we put a screen here. That screen's going to show up the light. It'll show a region of maximum intensity right in the center line here. And that region of maximum intensity will be, and we call this a bright band. This bright band will be twice the width of each of the bands as we move out. The intensity decreases also as we move out. And you'll see the intensity distribution here. Intensity is at a maximum right in the center. It's double the width of the next band, which is much smaller, much lower intensity, half the width, lower intensity again, half the width of the central bright band again. This is where we get to Young's double slit interferometer, two slit interference. We have, with the single slit, we have no interference occurring. We just have these diffracted waves. If we put two slits in this area, what we see, we have a barrier that has an aperture here, slit 2 that looks like, and an aperture here, slit 1. If this is light, they are very, very small, of the order of 10 to the minus 7 meters, comparable to the wavelength of the waves that we're seeing. This, you can't see it on this side. This plane wavefront comes in, strikes the two slits at precisely the same time, is diffracted through each slit at exactly the same time, and so we have waves that are in phase as they diffract through the two slits. Those two waves that are in phase interfere with each other. Okay, They're interfering with each other through these regions between here, this cone shape through here. And what we see on a screen on the opposite side, and I haven't, I'll just move this just a little bit. That's a little bit better. The screen on the opposite side, we will see once again a central bright band. That central bright band will be exactly the same width as each of the bands as they move out. The intensity distribution, the intensity of each of the bands is equal. They are as bright as each other. And we have these dark areas here, which we call dark bands. Screen will show dark and bright bands called interference fringes. So we call each of these an interference fringe. This is the central bright band. This is here we call this the first order maximum, the second order maximum. I might label those here. We'll start taking some notes now. Central maximum. I'll label these first minimum, and this is the first or first order maximum. This diagram is out of scale, is not to scale. In fact, the two slits are very narrow and very close together. This distance between the two slits is very small, less than 1 millimeter. In fact, if we're talking about Young's double slit interferometer, which is the device that we use in the next practical. Mr. Duverstein is writing the next practical this week. I aim to run the practical next Friday. Okay, that's at this stage. That's the aim. Some people have UMAT on Thursday or something like that. Or Wednesday, is it? Yeah. Okay, I'll just get a picture of the Young's double slit interferometer. So here's this device I've been talking about. What we see here, we're missing one part of the schematic of what's going on inside this interferometer, this tube. It's just a very narrow tube, 2 or 3 centimeters in diameter, I suppose. And right at the end, this is where we look through. So this is where the person will look through this way here. We have some crosshairs and a micrometer. I'll talk about those in a second. Most importantly, we have a single slit right at the front there. It's a very narrow, less than 1 millimeter single slit. And then a few centimeters along, we have the double slits. Okay, very narrow also, very, very, very narrow slits. Also very, very small distance between them. And somewhere in between here, we have the screen. I imagine the screen isn't very far along here. The distance between the double slits and the screen is very, very short. Okay, what else? Okay, so crosshairs. Now the crosshairs, when you look into this device, you will see something that looks like this. Okay. And what you can do by rotating this micrometer here, this little device on the side, is the crosshairs can move either left or right across the bands. The micrometer has graduations on it, and so you can measure how far you move along here with very fine precision, down to the micrometer, of course, micrometer. And what we will do in this practical is we will move the crosshairs across the bright bands to measure the distance between the centers of two of the bright bands. If we know this distance, then with some formulae that I'm going to give you shortly, we can calculate the wavelength of the light. We can calculate the distance between the screen and the slits. Okay, we can do some calculations. What I've tended to do in the past, instead of trying to find the center of a bright band, because these bright bands drop off basically nearly to zero very quickly, it looks like a almost a sharp line to us, to our eyes. I usually go from one side of a bright band to the same side on the next bright band is the best way to measure the distance between the centers. Okay. Okay. Difficulty that students have is using the micrometer. As you rotate this, you might rotate this several times to go from here to here. 2 or 3 times. You might actually do a full rotation. You have to count how many times, and you have to measure the distance. Students traditionally find this difficult. I find this difficult to do, especially if I'm trying to look into the magnifying eyepiece and measure at the same time. It's good if you work collaboratively during this practical to do this measurement. Okay. Did I mention last lesson also that these bright bands, the center of the bright band is maximum intensity, where the most constructive interference is occurring, maximum constructive interference. And the center of the dark band is where maximum destructive interference occurs. So essentially we've got our brightest here, and we have no light right in the center here. Everywhere in between, we're reducing down from very bright to very dim. We see this as a pretty sharp line because our retina doesn't register the light that's occurring through here down to the minimum. Okay, there is light, there are photons, or there are waves arriving in these areas, just not very much. Okay, not a lot of light. The next diagram, I'm not going to draw again. Here's another schematic of what's going on inside the interferometer. Now, we have a monochromatic light source here. The monochromatic light source could be, how do we get monochromatic? Does anybody know how we get monochromatic light sources? Shh, everybody else, please. Yeah, you could do. Yeah, you could use a filter that blocks. What you tend to do is use several filters, and to get it down to a very narrow band. It's near impossible to get one specific wavelength. Even laser light has a region. I think the minimum I read somewhere was the minimum they could get was a range of about 100 hertz, so which is pretty good. Pretty good. But we're not getting one wavelength. With discharge tubes, where you have a gas inside, of course, if you look at the back there, if we had lithium in a discharge tube at the top, I can see from this distance, at least two bands that you would see, two wavelengths of light, okay? And for each of those bands, there's probably an infinite number of, if you could break it down enough, there's an infinite number of wavelengths, essentially, that you would see there. Hydrogen, where is hydrogen? My eyes aren't that, oh, it's most of the way down. It's about 10th there. I can see a red and I can see a blue. I think there's two purples, is there? I can see one of the purples there. There's another one that's a bit more dim. Yeah. Yeah. So if we had a hydrogen discharge tube, then we're going to see several wavelengths. It's not monochromatic, okay? We'll talk about why that is later on in the course. Monochromatic light sources, generally what we do is we use lasers. I don't like using lasers. Can anybody see why from this schematic diagram and looking at the Young's interferometer here, why I would be reluctant to use a laser? Yeah, they are. It's a very, very fine beam, yes. However, we would have the situation where, of course, I'm sending laser light, and pretty fine laser light, yes, but it might be of the order of this into that interferometer there, okay? Maybe that's a little bit thick. We'll make it a little bit thinner, okay? We're sending laser light into this interferometer. Where is your eye with respect to this? Right over here, isn't it? The diameter of this tube is only about 2 or 3 centimeters. If you knock this across, that laser potentially could go straight in your eye. It's a helium neon laser, not particularly powerful, but at the same time will do damage straight away. Okay, so we're not going to use lasers. Any other ideas about what we might use? LEDs, yeah, LEDs are good. Yep, LED. Light emitting diode. Light emitting diodes emit very close, well, no, like I said, exactly with lasers, not one specific wavelength, but a narrow band of wavelengths. Okay? And so that's our monochromatic source. We send it through a single slit. Why do we send it through a single slit? I'll keep it red. Yeah, it diffracts through, doesn't it? Okay, we got diffraction occurring through here. I know my arcs aren't that good. And essentially, so what we have is by diffracting it through, we hopefully have this wave hopefully have this wave monochromatic and falling on each of the slits at precisely the same time. Okay, so that when I know I've not drawn this very well, but they hopefully fall on this slit at exactly the same time as this slit, and then we'll have a light diffracting through and interfering in these regions through here to form an interference pattern on the screen. Here's the intensity distribution. Here's a graph of the intensities. You'll notice they're all approximately the same. You'll see if you get an interference pattern, you'll see that the intensities are very similar. I'll just remove these here. These two lines here, so why have these two lines been drawn in here, do you think? What if I drew, to start with, if I drew a line to here from slit 1 and a line to here from slit 2, when will they arrive with respect to each other? The diffracted waves coming through. At exactly the same time, somebody said yes. They will arrive here at the same time. And we see, and so what we're going to see is a path difference of how much? A path difference of 0 for the green lines, okay? And so we're going to see constructive interference at this point. What about if, I'll remove those and draw them to, yeah, P1, it says. Okay, so to P1, what's the path difference there? Can anybody see straight away? Use your interference pattern. What is the interference pattern telling you about the path difference between these two? Half a wavelength, isn't it? Yeah, that's right. So half a wavelength path difference between, because of course S2 here has to travel half a wavelength further than S1 does to reach this point. And we have those two waves arriving out of phase by half a wavelength. Therefore, we have destructive interference and a point of minimum intensity right at that point there. Okay? If I then draw lines to P2, this is becoming more obvious now. S2 has a larger path difference, a larger distance to travel than the light from S1. And so we have a path difference of how much? Notice that we have a bright band there. The first bright band, 1 wavelength. Okay, path difference of 1 wavelength to this point. Okay, so I'll just yes. No, I won't. I'll just leave this conceptual. We'll go on to the next diagram. Any questions there? Now, in the past, I've drawn this diagram, and there is value to drawing it because we build it together. This is examinable. I did see this in a recent exam. I'll just familiarize you guys with this diagram before we move on. Here, once again, we have a monochromatic light source, a single slit. The waves diffract through. They strike the double slits at exactly the same time. The waves diffract through those double slits, interfere, and then we have a screen to see what's going on there. We have an interference pattern as a result. We have a central maximum at P0. Okay. And then what they've done in this diagram is they've chosen some point P out here. It's just an arbitrary point. For the purposes of showing you what's going on here geometrically so we can see. Can you see straight away the path difference between those two light waves? Can anybody see that? Path difference between the two waves. Well, look, from slit S1 to P is exactly the same length as P to D in this case, okay? And this would be, this area here, S2D, this line segment, would be the path difference between the two waves for that point P there, okay? Let's go through the proof. It's not gonna... It's not going to fit very well. I think I need to leave it that size so you can see what's going on best. Okay, so first thing to look at is this here. This point M to P. Okay, that point M to P and that point M to P0, and we have some angle theta in between those two in between those two line segments. Okay, so I'll write that think. So you can follow along closely. Line segment M P naught and line segment MP have an angle theta between them. Okay. One thing that we do point out once again is that this diagram is definitely not to scale. This distance here to P is a very, very, very short distance. Okay. Also, the distance between S1 and S2 is a very, very short distance, less than a millimeter. From that, you can say that this angle theta is very, very, very close to zero. It's not a very big angle at all. All right. Have a look at the line segments here, S2P and S1P. The path difference between those two, S1P and S2D, path difference, we'll call delta S is equal to S1P, actually S2P, S2P minus S1P equals S2D. Have a look again. Make sure you understand what I've just said. I found the path, I've just shown the path difference there, that distance there, S2D. And it's just simply S2P minus S1P. We're left with this. The triangle S1 DS2, there's a little triangle in there. This angle here, DS1S2, is also equal to theta. Can somebody tell me why that is? Geometrically. In the triangle S1, S2, D, the angle D S1, S2 equals theta also. And the angle between two lines is equal to the angle between their normals. So have a look at the angle here, MP naught, is between MP naught line segment and MP line segment, theta there, okay? DS1 is normal to MP there, okay? You see that? DS1 is normal to MP, or MP is normal to DS1. And S1, S2, these two here, that line segment there, is normal to MP. Okay? And the angle between two lines is equal to the angle between their normals. If you missed it, take my word for it. I have to get this right, this next part. In the triangle S1PD, S1 up to P, down to D, angle S1PD, so the angle right at the top here, up at P, this angle in here, is very small, okay? Because this distance is very small here, and this distance here is very small also. So we're talking of angles less than 1 degree. Very, very small in here. Angles P, S1, D, so this angle in here, that point, and PDS1, this angle here, these two angles in here are very close to 90 degrees. Okay? And I know that it doesn't look like that in this diagram, but because this distance here is very small and this distance here is very small, then these angles here, these two angles here, are very close to 90 degrees. Greater than 89 anyway. So this region here, from that, we can say that this little area here, this little triangle we're really interested in, that angle there is very close to 90 degrees from that. I know there's a few assumptions here, but we know that it's very close at least to 90 degrees. Therefore, and I don't want to move down too far, I can move down to there. In triangle, S1, S2D, sine of theta is equal to opposite S2D over the hypotenuse, which is S1, S2, I'll say S2, S1. And S2, S1 is equal to what? Well, they've already defined that distance between the two slits, S2, S1, as this distance here, D. So, S2, S2, D is equal to D sine theta. Okay, S2D is equal to D sine theta. S2D there is equal to this distance here times sine of theta as S1, S2, S2, S1 equals the distance D. Okay, that's not a difficult one there. And so what is S2D? Going back to our original, what is this here? Path difference, isn't it? Yes, thank you. Therefore, path difference is equal to D sine theta. Or the path difference is equal to the distance between the two slits multiplied by sine of theta. Is anybody still drawing that diagram? No. There's something other. Yes, those people that have got the new the new textbook also. I forgot to mention. Are there any questions about that? Does anybody want to? Last year there was some disputes. Some people, not that there should be any. I know it's not perfect mathematics, but it's very close. Those people that have the new textbook, this bright region in the center here is off, and it's actually they've got it as a dark region. Everything else is correct. Okay, so all of the explanation underneath this diagram is correct, except what they've done is they've taken this bright band or this interference pattern, and they've shifted it so that there's a dark band over P0. That's of course not right. Yeah, the new edition is not good. And it's only one thing that we've found, that's all. Somebody pointed that out. That wasn't in this class, was it? That was the other class? Yeah. Somebody following along. Oops. Next thing, we're going to move on. Okay, so that's an important one. Path difference is equal to d sine theta. One last thing, and then we'll do a problem. Fringe separation. We call this delta y. You might have noticed it in I think it's in the diagram there. Fringe separation is delta y, and actually what they've shown is that's to P2. Oh yeah, okay. So P1 is a dark band. Remember, I'll draw it in just so you can see what's going on there. So this might be a dark. Actually, I'll do it all. Is a dark band, and then we have a dark band here. Okay, and this would be a bright band in the center here. P2 is delta y is the distance between the centers of the two bright bands, and so that's measurable, of course, with our micrometers. At P2, what's the path difference? Bright band, dark band, bright band. One wavelength, isn't it? No? At P2, d sine theta equals lambda, the wavelength of the light. Okay? L is the distance between the double slits and the screen. L is the distance between the two slits and the screen. Oops. Another assumption, you math students will be horrified again. Because this distance is small, and the distance here is small, and this distance here is small, they're going to say this. Sine theta is approximately equal to tan theta. Because the distances are small. You don't like it? Oh, very small. I don't like it either. Very small. It turns out that we can make these assumptions because we're, for the purposes of our calculations, these work quite well in our course calculations. Okay. What's that? He did. Yes. P0 MP2. Okay, so P0 MP2. So I'll draw another line in there. Okay. Oh, cancel. P0 MP2. Tan theta we're almost finished. It's equal to the fringe separation on L. Tan of theta equals delta y on L. I'll show you that in a second. This angle in here, this angle theta in here, tan of theta is equal to opposite delta y over adjacent L. Okay. And d sine theta equals lambda. This is at P2. We get from that d delta y on L is equal to lambda. And the fringe separation delta y is equal to lambda L over D. And that's not examinable, that proof. But just remind you that the last one is. For fringe separation. Delta y. Oh, I didn't realise we were out of time. Sorry. I've talked the whole lesson. But we did get through it.